Kalyan, please send the message to all the students to attend the class. Only 45 students are there.
Yes, sir. Yes, sir. I will.
Okay, today I will take up to 3:45. I would like to leave before that because we are going to have a MTech program today. Today students join today and orientation program. So I'm teaching a couple of one subject, advanced mechanics of solids. So I have so to be there at least 3:30, but I would like to go 3:45. I would like to we have to go up to 3:45. Then I would like to leave the class. Okay. Yeah, are you able to see my PPT? Is
Yes,
it clear? Okay.
Yes, sir.
So yesterday we completed up to this. Today we go for the few problems. I mean, this is a very simple problem, and whatever we discussed yesterday, last couple of classes, concept only. Very simple problem. We no need to spend more time in this problem. Just I tell you the concept, and you can do it your own. Okay. See here, the first problem. I mean, a coil chain of your crane required to carry a maximum load of 50 kilonewton is shown in the figure. I mean, find the diameter of the link. So find the diameter of the link. I mean, link stock. If it is permissible tensile stress in the link material is not exceed to 75 megapascal. Okay. Very simple. Now our aim is to, this is I mean the chain hook, the chain we are using the crane, we are using the link stock, the dimension we would like to design here. I mean, here the permissible stress is given, permissible tensile stress is given 75 megapascal. This is a very simple problem. I mean, P, what is stress is equal to P by A. That's all. Now they have given the load, how much load we are going to use, how much load we are going to access using this crane hook. Using this crane link. Okay. In that 50 kilonewton they have given. Then the stress is given, permissible stress is 75 megapascal. Then you can easily find out the diameter of the dimensions of the link stock. We would like to find out the dimensions of the link stock. Then this is already given. Then A is equal to pi by 4 d square. From this, d is equal to what? Very simple problem. I mean, this is 30 mm. Now I come to the next problem. I mean, anyway, I just do it here. See here. I mean, area is pi by 4 d square, right? And what is this? I mean, force is equal to, force by area, right? Then sigma into A is equal to P. P is given 50 kilonewton. Then sigma is given pi by 4 d square is equal to P. From this, d is equal to what? What is d? Dimensions of the link is what? Then second problem, a cast iron link as shown in figure. See here. I mean, it's required to transmit the steady tensile load about 45 kilonewton. Find the tensile stress induced in the link material as shown in the figure, as shown in the design. See here the particular region of the interest. I mean, what is this? I mean, here we have to find that what is the tensile stress acting in this region. What is the tensile stress is acting in this region? That's what our intention now. Now see here, this is also similar problem. Similar problem. I mean, very simple. See here. Erase it. Okay. Now, I mean, the first one, the area is given here, 45 into 20. This is, you can consider A1. And the another area is given here for, this is nothing but, I mean, the side view, you can see, able to see the dimensions of this mechanism. I mean, 40 inner dia, this hook, this dimension is 40 and 75. Okay. Then you can find out the area here, A2. Find out the area A2. Then we are able to find out what is the stresses are, stresses are acting. What is the various stresses are acting in this region and in this region, A1 and A2. I mean, A1 is nothing but the cross section AA, A2 is nothing but cross section BB. Okay. Now this is the stress acting in this region A1, in this region AA, I mean 50 megapascal. But in the region A2, BB, cross the region of BB, the stress, how much stress is acting here? Now we know the area. This is a projectional area. Just to see that projectional area here. So 40, 75 minus 40 into 20. 20 is given width of, the thickness of this link. Okay, cast iron link. Then we are able to find out the area, 700 Newton, 700 mm squared. Then find out the corresponding stress. Corresponding that region, what is the stress? Then, corresponding the region stress is 64.3 megapascal. Then how do we reduce the stress here? How do we reduce the stress here? If I would like to reduce the stress, what I should do here? Because we already studied in the earlier chapter, wherever the curved surface, the corner surfaces are there, then the stresses will be, stress concentration will be more, as well as failure rate also possible. Now in this case, how can I reduce my stress? Without changing the outer dimensions of the shaft, outer dimensions of the link, outer dimensions of the cast iron link, how can I reduce the stress in this region? How can I reduce the stress in this region? Anyone, please? We have seen already in the earlier chapter flow lines, stress flow lines, using the fluid flow analogy, right? In this region, we would like to reduce the stress. Then, but now see here, now this region, this region is more stress. Less stress, 50 Newton per mm square. But when you consider this region, the stress is more. Then I would like to reduce the stress. I would like to reduce this at least less than 50, at least equal to 50 or less than 50. What is the possible? Any idea? Yeah, very easy, simple question, boss. Don't spend more time. Any idea?
Sir, increasing the diameter of the hole, sir.
Yeah, increasing the internal diameter. Increasing the internal diameter. No, reducing the internal diameter. Reducing the internal diameter. Yeah, please 1 minute, but yeah, you take. I have class. You take the system if you need. Okay, reducing the internal diameter of the link. Okay, so this way we can reduce the stress in this region of interest. Okay, and now I come to the another problem, a simple problem. Okay, two plates 16 mm thick are joined by double riveted lap joint as shown in figure. The rivets are 25 mm diameter. The rivets diameter is 25 mm, and the crushing stress induced between the plates and the rivets if the maximum tensile load 48 kilonewton. Okay, now our interest is to find out the crushing stress acting in the, how much crushing stress is acting in this rivet region. Okay, the crushing stress, this is also very simple problem. The load is given already 48 kilonewton and thickness of the plate is already given. Thickness of the plate is given 16 mm. See here, 16 mm already given. Thickness of the plate is given 16 mm. Then you can straight away substitute in the equation formula. You can get it. P by D into T into N. This is area. This is number of rivets. N is equal to. Then finally 16 Newton per mm square. So okay. Now come to the another problem. A journal of 25 millimeter in diameter supported in sliding bearings has a maximum end reaction 2500 Newton, and assuming the allowable bearing stress, 5 Newton per mm squared. Find the length of the sliding bearing. sliding bearing. We would like to find the length of the sliding bearing. This is our bearing, right? I mean, this is the bearing. This is the journal. This journal. This is the bearing. Okay, now this is also direct formula what we discussed. Our intention is to find out what is L. What is L? Length of the journal. What is the length of the journal? Okay, now see here. I mean, we know the formula, right? A journal bearing pressure is nothing but bearing pressure sigma is equal to P by L A. Not sorry, L into D. P by L into D. DL because this is a projection area, D into L. Okay, now that I mean they have given the load. How much load is they have given? 2,500 Newton. Okay, and the bearing pressure also given 5 Newton per mm square. Then directly substitute. Then you are going to get the journal length of the journal is 20 mm. Length of journal is 20 mm. This kind of question you may expect in the objective. You may not expect in the our descriptive type exams. Okay. Now the triaxial load problem. This is see this problem. Just recap this. You might have been studied. I don't know whether you studied this kind of problems. Okay. Anyway, a cast iron flat 300 mm long and 30 mm into 15 mm 50 mm uniform cross section. I mean, it is acted upon by the following forces uniformly distributed over the respective cross section. I mean, 25 kilonewton in the direction of length. 25 kilonewton. This is a tensile in the directional length in y direction, and 30. I mean y direction, and 350 kilonewton direction of width. 350 kilonewton direction of the width in the x direction. Okay, x direction. It is a compressive load, and 200 kilonewton in the direction of z. It's like a tensile. Again, tensile here acting. I mean 200 kilonewton. This is a tensile. Now first find out the these dimensions of the block. That now dimension of the component you know very well. Now our intention is to find out how much change in volume while this triaxial load is acting in this component. Now very simple, sigma x find out based on this direction, based on the load acting direction, corresponding plane you consider for finding the area. Okay, for this is the x plane, this is I mean y plane. Yeah, sorry, this is y plane. This is x plane is here. X plane is here. This is the x plane. Okay, I mean this is the y plane. Y plane is here. Now this is the z plane. Sorry, this is the z plane. Then this plane dimensions already given. Then find out each plane what is the stress component. I mean based on the stress direction, the load direction, you can find out either compressive or tensile like that. Now first sigma x is compressive with sigma x is compressive stress, and the sigma y is in tensile, and the sigma z in again tensile. Now I mean yesterday we studied, right? Now we are going to strain. We are going to find out the strain. I mean before finding the strain, net strain or total strain or volumetric strain, before finding the volumetric strain and each direction we are going to consider this consider to finding the strain. Then once we complete with respect to x-axis, what is the strain component? With respect to y-axis, what is the strain component? With respect to z-axis, what is the strain component? Finally, we are going to sum it all together. Then net strain will be calculated. Okay, I mean what is the right? Sigma epsilon x or ex. You can some books they mentioned ex, some books and epsilon x. Then what is the formula we yesterday discussed? I mean 1 by e into sigma x minus mu into sigma y minus mu into sigma z. Now mu is nothing but here mu is nothing but 1 by m. Okay, now here this is a minus. I mean usually in x direction the stress component is negative, hence the stress component to x direction, sorry, compressive x direction compressive stress, hence it will be a negative sign here. Only one thing I am explaining, remaining thing you can do it yourself. And y direction mu into sigma y, I mean this is E is a common to all, and Y direction it's 10 Celsius, then it's the the sign it won't change, and Z direction again tensile, the sign, the minus sign won't change. Then this is the strain component with respect to x direction, okay, principal direction with respect to x. Now similarly you can find out sigma y also, epsilon y is equal to 1 by E into sigma y minus mu into sigma x minus mu into sigma z, okay, mu into sigma z. Okay, now already you know the stress component. Substitute here, you are going to find out in terms of mu. In terms of mu is nothing but 1 by m. Now add, this is with respect to sigma z, this is with respect to epsilon y, this is with respect to we are considering three principal directions. In the three principal directions with respect to x, with respect to y, the strain with respect to z. Now all sum it, you are going to get volumetric strain. Volumetric strain is nothing but the epsilon, EV is equal to epsilon V is equal to epsilon x plus epsilon y plus epsilon z. Okay, now from this we are able to find out what is this change in volume of this change in volume of the material. This is epsilon V. Finally we are able to know, so epsilon V is nothing but minus 0.00000314 strain in volumetric strain. Then you apply the general formula, epsilon V is equal to del V by V. From this we can understand how much a change in volume, we can calculate how much change in volume. This is a change in volume of the material. Okay, change in volume of the component. So whatever we are designing, we should consider during that time if the component subjected to different load, triaxial load or biaxial load, how much a change in volume going to happen. Based on that we have to design we have to decide our load with component in the component, in the various loads in the component. Now I come to the one more interesting problem. See here, as a mechanical engineer, we are using a lot of bolt and nuts, right? In the nuts, this is the see the problem. A steel rod of 20 mm diameter passes centrally through the steel tube 25 mm. This tube is 25 mm. 25 mm already given, 25 mm internal dia, and outer dia of the steel tube is 40 mm. It is internal dia. Outer dia of the steel tube is 40 mm, and the rod, inside rod, the rod is nothing but our bolt. Our bolt, we are saying the rod here, that is 20 mm. That is 20 mm here. Okay, the tube is 750 mm long, and the closed by the rigid washers. We are using rigid washers. And the negligible thickness of the washer thickness is negligible, and which are fastened by nuts threaded on the rod. Now the both end of the tube now tightened with the help of the nut, with the help of the bolt and nut. The rod end is made with the threaded portion. Okay, now when you are tightening, they have given the condition. The nuts are tightened until the compressed load, compressed load on the tube 20 kilonewton. Now calculate the stresses in the tube and rod. Already when the nut is tightened 20 kilonewton, the force is acting on the tube. Now tube and rod. Now what is the question is, find the increase in the stress when then one nut is tightened. Now already this is a tightened. Now I would like to tighten the nut again 1/4 turn, quarter turn of the relative other nut. Then what is the stress is created? What is the external, what is the more stress created in the rod and the tube? That's what my intention to find out what is that. Okay, now see that the metal property is given. Young's modulus is equal to 200 giganewton GPa. Okay, now area of the rod, right, I mean, area of the rod is pi by 4 into 20. I mean, converted into meter, 0.02 mm square. This in terms of meter square. Area of the steel tube, you know, they have given internal dia and OD and ID. Be able to find out this, I mean, diameter of the tube. And I mean, now compressive, where is the compressive load? Compressive load is acting on the tube. I mean, tensile load acting on the rod. Okay, but how much compressive load acting on the tube, that must be equal to the same amount of the tensile load acting on the rod here. Okay, now that is the one condition, not condition. It's based on this mechanism. We can easily identify that. Okay, now the bar, the tube is subjected into compressive load 20 kilonewton. The same time that rod is subjected to tensile load 20 kilonewton. Now we know that, right? Now we know stress at the rod, stress into, I mean, tube stress into area of the tube. It will give the how much load is withstanding, and rod stress into area of the rod, okay, is equal to 20 kilonewton, right? At the present condition. Now we would like to find out what is the stress. From this relation, we are able to find out the stress, how much stress is subjected in the nut and rod. Now, see here, this is a 20,000 divided by, I mean, we know the area of the tube, we know the area of the rod, okay, rod, then substitute here, then how much stress is subjected, how much stress is subjected in the tube? 26 megapascal. I mean, MPa, 26.1 MPa stress is subjected into the tube. How much stress is involved in this, subjected in the rod? I mean, 63.6 megapascal when the mechanism is subjected into 20 kilonewton. But our intention is not that one. Our intention is further I am going to tighten the nut. Now further I am going to tighten the nut. What is the further I am going to tighten the nut 1/4 quarter turn of the relative to other, either this nut or this nut. I am going to turn to 1/4 turn, 1/4 turn, and then they have given the condition also. There are 0.4 threads per mm. I mean, 0.4 thread per mm means that the displacement of the nut they have given here. I mean, now the distance traveled while you are rotating quarter turn, how much distance travel they have given. This is a quarter turn into, they have given all the dimensions, the movement of the nut, okay, in the longitudinal direction while apply the turning moment, right? This is 0.000625 meter, mean around 0.625 mm. While, I mean, initially it is the nut is subjected, I mean, the tube and rod already subjected to 20 kilonewton force. But now again, I would like to tighten the mechanism. Then this mechanism, I mean, we restricted it to 0.625 mm. Then now we are tightening the bolt. What is the force? What is the stress is acting? We'd like to find out. That is our intention. Now see here. Okay. Now in this very simple problem, it's not difficult one. Now see here. I mean, this when that nut movement 0.625 mm during that time, I mean, the rod is going to be a tension, extension, okay, but I mean, the tube going to be a contraction, right? Obviously. Now this apply this. Already, you know, I mean, already what is the stress in this region? I mean, stress. What is the force? What is this along? What is the deflection? PL by AE. PL by AE. In this case, I'm taking a sigma L by E. Sigma L by E. In the rod, okay, this is sigma PL by E, sigma L by E in the tube. Okay, now, I mean, E is a common, length is a common, both a nut and tube we consider. Then substitute this, simplify this equation like this, and now apply the condition. While tightening the bolt nut, I mean, the same force is acting in the bolt. I mean, bolt in the means in the rod as well as a tube. Okay, what is the difference? Only the rod is subject to tensile load and the tube is subjected to compressive load. That's what. Hence, I can write the condition like this. Okay, now take I mean, now this is this is our equation, main equation. This is equal to 0.625 mm. 0.625 mm. Now I apply. Now I'd like to find out any one of the stress. But here this is a two unknowns. I can't find it out. Then I am applying the condition. I would like to find out either stress in tube or stress in rod in terms of tube. For example, stress in tube, I would like to find out stress in terms of rod, or stress in rod, I would like to find out in terms of tube, right? Then find it out. Finally, the sigma rod, stress in rod, I have found it in terms of tube. Now substitute this. Rod, the stress, how much stress is subjected in the rod is equal to 2.438 times of stress in the tube. Then substitute this main equation. Now we able to find out the stress in the tube. Okay. Now we able to find out the stress in the tube. The stress in the tube is going to be 48.478 Newton per mm squared or megapascal. Now stress in the rod, then simply with this equation, once you find out the stress in tube, then you can easily find out the stress in rod. Stress in rod is 118 megapascal. So this is the, now when we are tightening the nut, 0.625 mm deflection, 0.625 mm compression in the tube, 0.625 mm compression as a compression in the tube as well as tension in the rod. So during that time, this much stress variation is going to be there in the tube as well as the rod. So this kind of information is very important when we are going to design our component. When we are designing multiple components, each component going to be connected in appropriate manner, either using bolt and nut or rivet joint or rivet mechanism or bolt and nut, whatever. Hence we have to this way we have to design our component. Even bolt, what is the size of the bolt, what is the size of the rivet, these things also we have to design in this way. Okay. Now I come to some fluctuating stress. What is the fluctuating stress? What is the fluctuating stress? Okay, anyway, anyone, what is the fluctuating stress? Guys, are you there in the meeting? I'd like to check how many people are there in the meeting. Only 57 are there. What is the fluctuating stress? Please, someone tell. Yeah, fluctuating stress. What is the fluctuating stress? Hello? Okay. Fluctuating stress. Whatever we studied as static load, and now we are we touch the fluctuating stress, then we are going to solve the problems. In the more problem we are going to solve in the upcoming classes. Okay. Once the external load applied to the element has been determined, which stresses are generated within the element, right? Once the external load applied to the element, that must be determined which type of stress is developed in the component, right? Whatever we discussed earlier, the calculation of tensile load or tensile stress or compressive stress or shear stress based on the tension and based on the compression load based on the shear load, right? But bending stress due to bending load. Well, torque means torque means due to the power transmission or twisting moment, right? But fluctuating stress is machine often considered the sinusoidal form because of the nature, while the machine of when the machine in rotating, when the machine elements are in rotating, now the stress variations are characterized by 5 components. One is sigma max, right? Sigma max and sigma mean, right? Minimum stress, maximum stress, then average stress. Sigma m is mean stress, not minimum, mean stress, average stress. Sigma a is amplitude of the stress. How many stress component? while the component is functioning or operating. These are these 5 ways we can define the stress in general term: sigma max, sigma min, and sigma minimum, sigma mean stress or means average stress, and this is a stress amplitude. And last one is stress ratio. Stress ratio is nothing but sigma mean divided by sigma max. Okay, now see here, if you know any pair of stress, either sigma max or sigma mean, if you know that, you can find out other parameters. Okay, the maximum and the minimum stress obtained, it can be obtained by theoretical analysis used from finite element method. When we are simulating your design, when you are designing the new component or mechanical system, that can be done with the help of the FEM, right? While you are doing that, you can see the maximum stress, minimum stress in the software, right? While designing the software, while modeling the CI, while doing CI model, then you can see which portion of the component subjected into maximum stress, which component is subjected to minimum stress, such a way that you can see that. The experimental measurement also you can understand where is the maximum stress, where is the minimum stress, like that. Now we will see the different types of stresses. Or just we touch this. We are going to discuss in detailed manner in the next chapter, but I would like to explain here itself some of the things, because we are discussing the type of stresses and loads and different types of stresses and loads. We are already discussed. Similarly, simultaneously, I would like to give an input about the fluctuating stresses in this topic itself. Okay, now sigma mean stress is sigma max plus sigma mean by 2. This is sigma amplitude, stress amplitude. Stress amplitude is, sigma max minus sigma mean divided by 2. How we are seeing this, we'll see that one by one. Now, as we know that, what is a static load? What is a static load? We already discussed in the earlier class. Static load means that when the stress amplitude doesn't change with respect to time as well as direction. But initially, we cannot expect that. If suppose any machine member or component subjected into load, initially it will start from 0, then gradually it will reaches to some point, right? Because if suppose it's taking slowly, the stress value is slowly increasing, after it may be stable, right? Then it will not change in the direction. It will change the stress amplitude. Here, the stress magnitude doesn't change with respect to time. Hence, this is under static load condition. Why here changing? Anyone tell me the reason? This is a basic question. Why now changing from here? Gradually changing. Why we are saying gradual changes? Actually, we are telling that static load means it should not change, right? It should not change that stress magnitude as well as time. We are telling that. But why we are telling this region? Still we are considering this region. Why this region still we are considering? Please, someone reflect. Hello? Yeah, guys.
Sir, then we have to do the work energy and impact analysis again.
Yeah, you are correct. But the second word, impact analysis, don't use that word. First, whatever you said, correct. Because if we are, any machine component at the initial, while operating, when the machine operation is performed, when the machine is performing some process, the component will not reach immediately high stress value, right? Gradually it will be increased, right? Because suppose it suddenly increases the stress value, that is nothing but impact load. So impact load is not advisable for designing any mechanical component. Okay, that's what we are considering here. For at the initial stage, beginning stage, we are considering the stress level is gradually increasing. After some time, it's a study. Here the static load in this region, the load, whatever we are applied the load, the static load, now the load or stress doesn't change with respect to time. Okay, now I come to the fluctuating stress. The stress is generated in the element which is subject to slowly applied load. I mean, that's what slowly applied load. I mean, that is held in constant value. The stress versus time due to static loading. Okay, now this is the fluctuating stress. Well, we will see the three types of fluctuating stresses. Briefly, we'll see that. Now, what is the first one is I am considering completely reversed stress. This is sigma max. I mean, this is sigma max plus 10 megapascal. This is minus 10 megapascal. This is completely reversed load. Okay, when the subject, see here, this is the shaft subjected into bearings, two-side bearing. Now the shaft is rotating. I mean, this shaft now this top portion now subjected to compressive. When the shaft this portion going to be here, then the shaft subjected to tensile, right? When the shaft region coming again back to top region, then that portion going to be subjected to compressive. Then the cyclic manner the stress is acting in the component. Hence, this is completely reversed stress, because when this top region subjected to 10 megapascal compressive, the bottom region subjected to 10 megapascal tensile, like that manner. Now, in this case, what is the sigma mean? The sigma mean is 0. So this kind of question you may expect in the objective questions. Okay. Now I come to the next one. I mean, repeated and fluctuating stress. I mean, in the repeated and fluctuating stress, the minimum stress is 0. Minimum stress is 0 in the repeated stress. In this stress, here sigma is, for example, 10 megapascal. Here sigma is equal to 0. Okay. I mean, what is the example for this? Any example? Any example for this?
Spring weight, sir. Weighing spring, sir.
Yeah, exactly. When you are apply the load, it will be expands. When you leave the load, it will come to 0, right? The another example, teeth, gear tooth. Now this is the one gear, okay, pinion. Okay, I'm considering this is a pinion. This is a gear. Now see here, now this, I mean, this gear 1 subjected into either compressive or tensile, whatever. Now this is now subjected into some stress, but number 2 is ideal. Now 0 stress acting in the teeth. Now number 3 also 0 stress acting in the teeth. After some time it will become here. The 2 again it will become here. Someone of the gear teeth going to be engaged with the pinion teeth, right? Hence we can consider as a meshing gears. Meshing gears is a good example for, I mean, repeated stress. I mean, repeated stress here, I mean, sigma mean is 0, but sigma max is some value should be there. Then this sigma mean is equal to sigma max by 2. Okay. Now, I mean, fluctuating stress. What is the example for fluctuating stress? I mean, I have given already example, but can you tell me some other example? Fluctuation is an alternating stress, is a non-zero mean value shown in this figure. Non-zero mean value here means mean value is going to be non-zero mean. Any example? Fluctuating stress. Fluctuating stress. Any example? I mean, piston rod inside the cylinder, IC engine, no piston. That is fluctuating stress, right? Okay. Okay. Now I come to this. Now what is 10 now? Okay, we start this. Oh, 347. Okay, I stop here, and the remaining things, please, next class we start 8 to 9:30. Please kindly request you cooperate you. Okay. So I have to attend the meeting. Guys, in the next class we discuss the problems as well as remaining theory and problem. We are going to discuss in the next class. Actually, as per the schedule, actually I don't have that. I am preparing the schedule now, lecture schedule. Once I prepare it, I give back to you and get back to you, no problem. But earlier, who taught this subject, I gone through that. So we are going at right speed only. Don't worry. My plan is before CRC meeting, we would like to complete the second chapter. I mean, next class and next class, and there at least two class may be required. 2 to 3 class for second chapter. Then 4 to 5 class for third chapter. That's all. I mean, at least 3 chapter. I mean, the 4th chapter we should complete. Half of the chapter we should complete for the midsem exam. That's what I told you in the beginning. So same thing we can do it, no problem. So now we have enough basics we discussed, right? Then we are going to enter into the component design in more depth in the upcoming classes. Okay, I mean, few basics are there. We will discuss in the next class first off, then we go to problems. I mean, I would like to know, did you study the principal stresses in your second year? Yeah, please, someone reflect.
Yes, sir.
Okay,
Yes, sir.
Then no problem. I'm not going to waste of time. Just I touch the basics, then we go for the problems directly. Okay. Okay, guys. If you have any doubt, please go ahead. Otherwise, I close the meeting.